So the goal today is to do a very simple calculator for water content and bulk density of granular materials. We're going to do this calculator on Python, but before we go to the program, I'm going to show you a little bit about the theory about what water content and bulk density is in granular materials. This is usually seen in soil physics and soil science when you take undisturbed soil samples, but it's useful for other types of materials in geology and in chemical engineering, a lot of other applications. But let's think about soil science for a second. When you take an undisturbed sample, for example, it's very common for us to take cylinders or cores, cylindrical cores. So you get a metal cylinder here, and you take it to the field, and you insert this into your porous material, your granular material, and then you extract the cylinder, and what you have inside here is the granular material will fill the inside of the cylinder. So we say that this is an undisturbed sample because to some degree it preserves the internal structure of the material. And the other thing about bulk density is that inside the core, inside this whole volume of the core here, you're going to have your solid particles, which are I'm indicating by these pink spheres here, and you're going to have pore space, which is empty spaces. You're going to have solids and you're going to have pore space. And this pore space, it can be filled by air if the material is completely dry, or by air and a fluid, usually water if the material is partially saturated, or it could be completely filled by a fluid, either water, oil, or other kinds of fluids in other kinds of materials. So the goal is to calculate the bulk density. What is this bulk density? I'm going to represent it as whole B. Is the mass of solids over the volume, the total volume of the material. If you're taking a cylindrical sample, the volume is the volume of the cylinder, but it's usually, sometimes people take samples in cubes and other types of shapes as well. But for us, it's usually we take it in cylinders, so let's consider the cylinder. So the mass over the volume is the bulk density. The bulk density takes into account the volume occupied by space, by not occupied by solids, and this volume can, like I said before, could be occupied by air or by water. Usually when we're talking about bulk density, we're talking about the dry bulk density. So we dry this sample usually in an oven at around 105 Celsius to extract the water. So you're left only with residual water tightly absorbed to the solid surface. But it is also possible to calculate the wet bulk density, which we'll be considering, it would consider the fluid inside this material. What is the water content? The water content is usually represented, at least in soil science and sometimes in hydrogeology, by the Greek letter theta. So you have two types of water content. You have a mass-based water content, which is usually called gravimetric. It's mass-based, it's mass over mass. In other fields, in fields other than soil sciences, this is usually represented in percentage, but in soil science is usually represented in mass over mass. So grams of water per grams of dry material. So we don't usually cancel the units here because we're talking about different things. And we have the volumetric water content, which is the volume of water divided by the volume of material, by the total volume. So volume of fluid over the total volume. So again, it doesn't cancel because we're talking about different things. And in other areas, the volumetric water content could be represented in percentage, but percentage is not recommended in, at least in soil science. I don't really have a big problem with that, but let's consider that when we're writing our code. So let's go to Python and see what we can do. So I'm in Vim here. I'm gonna execute. I have two windows here in my terminal, and I'm gonna execute. I'm gonna write the code in one window, and I'm gonna execute Python via terminal in the other window. So let's just clear here. You can use the idle, or you can use VS Code or whatever, or any other interface which you use to program, or developer environment, or whatever you use to program. I'm going to use Vim because I'm used to it. So let's write our program. Start. I'm going to put some comments here. I'm going to leave a space before here. If we need some libraries, some Python libraries, I'm going to insert it here. So I'm going to leave this open space here. I'm going to do a little comment here. This is not read by the program. It's just a comment for the program. So program to calculate volumetric better other content and bulk density. This program is going to get user input and output the results. So what will be the user inputs here? The user inputs are going to be the wet mass, including soil particles or granular material particles, water, and what we're going to call the tare, which is the mass of this cylinder here. So you have the total mass is the mass of the particles plus the mass of the water plus the mass of the cylinder, which we will call tare. So this is the total wet mass, and after oven dry, we're going to have the total dry mass, and we need also the mass of the cylinder, which will be called the tare. So you weigh your cylinder when you get from the field. When it's wet, you dry it in the oven, remove the samples, the soil from inside, and then you weigh the cylinder. You can also weigh the cylinder before you go to the field. It doesn't really matter. So the first input that you will need, so let's write here, user inputs. Let's get the total mass. It's called mtotal wet. So I'm defining a variable here. Because Python, it's a very simple language in terms of the syntax, you don't need to declare these variables before like you would need to in C, C++, or Fortran and several other languages. So the total wet mass will be, I'm going to use a function here, input, which calls for user input. And this is going to be printed on a screen when we run the program. So let's put enter total wet mass. Leave a space here. Let's put, I'm going to copy this here. Let's put the dry mass here. And let's put the tare. So if we execute this correct, we're going to have those three variables. So let's change this here to dry mass. Let's change this to tare mass. Let's see, let's just test if we did this correctly. So print, I'm going to print on the terminal mtotal wet, mtotal dry. Okay. So I'm going to save this. I'm going to go here. I'm going to run. The way I run is Python. Oh, one thing that I forgot to mention, I saved this file here as bd, the wc.py. So when I run here, I'm running Python. I'm going to call the program Python3, which is already installed on my system, and I'm going to run bdwc.py. So I'm running, and it's asking me for a total wet mass. Let's put 150.0, total dry mass. Let's put 100. Tare mass, let's put 35. Oh, I forgot the little mistake here. So I wrote the variable wrong. Let's try it again, see if there's any issue here. 150.0, 100.0, 35.0. So it's printing, it's correct. So let's just make this program a little better. For the user input, let's just put a line here. So this is how programs used to be done when you didn't have graphical interfaces. Like in Fortran, they should be done like that. Still are to a large extent in Fortran, C, and other old school languages. So we will need the tare. Other things that we will need here is the volume of the cylinder, but we don't have the volume of the cylinder, but we can calculate the volume of the cylinder. So we're going to need the diameter and the height of the cylinder so we can do the calculations. So if you remember from basic mathematics, we can calculate this total volume here if we know the height and if you know the radius or the internal diameter. So it doesn't really matter. So you remember that the total volume here, this total volume is pi r squared or times h or pi r squared pi d squared over 4 times h. So those two formulas are equivalent if you remember that diameter, it's 2 times the radius. Okay, so let's pretend that we know the height and the diameter or the radius. Oh, it's useful if we know it's not useful. We need to define the units here because the calculations vary according to the units. So usually bulk density would be given in grams per cubic centimeter or kilograms per cubic meter. Let's work with grams. Okay, so let's input now the variables of the cylinder. We're just going to copy this here. I'm going to paste and I'm going to change the name to diameter. Enter the diameter of the cylinder in centimeters. Going to go ahead and copy this here. I'm just putting, this is going to just print a line there just for aesthetics. It doesn't really matter. So let's call this here height. So enter the height of the cylinder in centimeters. So we already have most of the things that we need. Let's just test the program without printing anything. Just gonna save, switch to my other window and test it. Enter the mass, the wet mass. Let's say it's 150, 110. Enter the tare, 35, diameter 5 centimeters. Enter the height of the cylinder, 5 centimeters. So it's okay. We don't have any problems. So let's just call this here. Okay. Now we need the formulas. We need to do the calculations. So let me just copy this here. So this is going to be our output. Let's just do some calculations here. So what we need first is to calculate the total volume. So let's call the total volume VT. Now we're going to need the pi number to do this calculation, but we don't want to use like 3.14, etc. We're going to use it from a library from Python. So we're going to import the variable for manipulating numbers, numpy, and we're going to import it as np. So whenever I call a variable from numpy, I don't need to write numpy, I just write np. So np dot pi, so this is this here defines pi times the diameter squared. So in Python, those two stars here is the power operator. It's not the hat symbol like in other programming languages. Divided by 4. I put 0 here just because kind of you always have some problems with that in C, C++, so I'm just going to put here out of habit. Okay. Times height. Okay, so now we have the volume. So in this print here, let's just test our program. Let's call this here output. Just to. And now we're going to have several print functions. So in this print functions, the total volume of the sample is, let's put here, you can put the superscript and the subscripts here, but I'm not going to do that right now. Okay, and comma, okay, need to cut to close this here, comma vt. So if everything is correct, we're going to get the total volume of the core using this calculation. Okay, let's try again. Enter the total wet mass. We don't need this yet. We haven't used it. We're going to calculate the volume. So the tear also, we're not going to need this. Enter the diameter of the cylinder. Usually you see all sorts of diameters, but let's suppose it's 5 centimeters diameter. The height, it's also common cores with 5 centimeters diameter and 5 centimeters height because their volumes around 100 cubic centimeters, which is a convenient value. So we have a problem here. Let's see. I have a problem with the types of variables here. So yeah, that's exactly the problem. The problem here is that it's reading as a string, as character, or as a word. And what we want is that this is a number, an integer, or a float, or something like that. So let's try to convert this to float and see what happens. So let's call diameter equals float diameter. I'm gonna use the same numbers, the same names here. This is not good programming practice, so actually let's just call this diameter 1. So I'm converting this to float, which is a floating point operator. I'm going to try to do the same thing here with the height equals float height. So height, let's call this height 1. And this is actually a disadvantage in Python because in other languages you have to declare the type of variable beforehand so you don't get into with this sorts of problems. So let's try to run it again. The masses still don't matter to us because we're not doing calculations with them. So 35.0, enter the cylinder diameter, enter the cylinder height. So okay. So that was exactly the problem. So I converted the strings. I was writing 5, but it was reading it as a word or text or characters. And now I converted it to float, and here this is the result in floating point. So it's a floating point number. Okay, so now it's okay. Let's do the same thing here to the dry masses. I'm going to put this below here. Just going to organize the program here a little bit. I'm going to paste this here below to organize our program. Okay, let's do the same thing here. call this m total wet 1 equals float m total wet. All right, do the same thing here. I'm gonna copy these two here, then I can modify them. Okay, m total dry equals float, same thing here, float. I'm gonna copy this here so I don't have to type everything again. Do the same thing here. No, this is small, I can just write it here. All right, so let's just close this here. Okay, so total dry 1, tear 1. So they're all now floating point numbers, and I can do the calculations on them. So I have the total volume and what I need to do to calculate the bulk density is the particles mass or the dry mass over the volume. So I have to get this mass here without the water content and without the tear. So it's pretty simple. Let's go back here. So let's call bulk density. Let's call this dry bulk density, DBD, equals the m total 1 dry minus the tear 1, which is a tear, divided by VT. So now we have the bulk density. And now we do something similar here. P, the bulk density. Let's call this the dry bulk density of the sample is, and the value will be in grams per cubic centimeter. Okay, so the variable here that we need is the PBD, dry bulk density. So the whatever is in pink here, it's going to be printed in the screen, and in white here I'm calling the variables, and the blue here is with those hashtags here is comments, and print here and other comments that are in blue are internal comments from Python. So let's try again. Enter the wet mass 150, dry mass as an example here 125, tear let's call 35, diameter 5.0, height 5.0. I probably wrote something wrong here. Okay, so this is the problem. M total dry 1. Okay, so okay, let's try again. I'm gonna clear this here. $125, 100, tear 35.0, 5.0, 5.0. So now we have the total volume of the sample and the dry bulk density. This dry bulk density is pretty low, so because I'm just putting numbers, kind of sort of random numbers here, it's pretty low. And now we're going to go to the rest of the calculations, which should be pretty straightforward because we know how to do these things from the previous commands. So let's go back, just show you how you're going to calculate the water contents. What is this gravimetric water content? The gravimetric water content, like I mentioned, is the mass of water divided by the mass of solids, of solid material. What is the mass of water? The mass of water is the difference between the weight before oven drying, before drying, né? And the weight after drying. So the difference in weight when you dry is the water that goes out. So the gravimetric water content would be the water mass divided by the mass of solids. And the mass of solids is obviously, like we did before, the total dry mass minus the mass of the cylinder or the tear. Okay, so we can kind of use this formula here for the bulk density and adapt it. So the total dry mass minus the tear is the denominator. This is the dry mass of solids. I'm just going to copy this here. I'm going to paste here. Oops. Let me undo this here. Copy. Paste here. So what I have this over this here, but this upper term here is just the difference of the masses, the wet and dry masses. You could take the tear out in the numerator, but it doesn't really matter. So M total wet 1 minus M total dry. This is the wet mass minus the dry mass. This is the mass of water over the mass of solids, which is the dry mass minus the tear. So the tear. So this is the gravimetric water content. Okay, so same thing here. Let's just print here, copy this command here, and let's write the gravimetric water content of the sample is in grams over grams. I'm using large names here, but you shouldn't do this when you're writing programs because it makes life a lot more difficult. But I'm doing just for the sake of giving an example and detail and everything. I forgot to. This is probably too small, so let's just do this a little bigger for you so you guys can see it better. So now we have the total volume, the dry bulk density, and the gravimetric water content of the sample. Let's try our program once again. Just clear this here. Let me also put this a little bit better. So I'm going to run my program, enter the total wet mass, going to put a little bit more this time. Dry mass 125, enter the tear 35.0, diameter 5.0, height 5.0. Now we have total volume 98, dry bulk density 0.91, and gravimetric water content 0.27 or 27%, 27 grams of water for each 100 grams of material. Okay, so now what we need to do is to calculate the volumetric water content. The volumetric water content, in essence, like I mentioned here before, let's call it theta V, is the volume of water divided by the total volume. We already have the total volume. We could calculate the volume of water knowing the bulk density, the density of the water, and other parameters. But in soil physics, you could easily derive this formula. It's probably used in other fields as well. But the volumetric water content is the density, the bulk density of the material over the density of water times the gravimetric water content. So this is the simplest way to calculate this. I could derive this, but it's not the purpose of this video to derive this. Okay, so let's just use this formula here to calculate the volumetric water content. This here, as you know, is equivalent to the mass of water over the mass of solids. You can easily derive this from this relationship here, because you know that for almost any material, the density is mass equal volume. So if you isolate the volume here on this formula, you have mass over density, and you replace here, and you end up with this formula here. Let's implement this formula in Python. Go back to our program. I'm just going to copy this formula here because of simplicity. Paste it here. So we're going to need a value of the density of water. So let's put here in the declarations of variables here. Let's put a declaration of variable here. You could actually use it as a user input, but or you could calculate based on the temperature or a lot of other things. Let's call this water density, and if we're working in grams per cubic centimeter, it's approximately 1.0. Like I mentioned, you can calculate from temperature, but let's assume that it's around 1.0. So now the gravimetric water content is the dBd, the dry bulk density, divided by the water density I'm going to put parentheses this here. You don't need parentheses here, but just to make our code a little bit more readable. Times the gravimetric water content. Okay? So this here is the volumetric water content. So let's say the volumetric water content of the sample is in here. We're working with cubic centimeters per cubic centimeters. So this here is volumetric water content. Okay? So let's just put line numbers here to see how big this program is becoming. So around 40 lines, which is not too much, it's not too bad. Okay, if you're working with kilograms per cubic centimeter, this here would be around 1000, but we're working with grams per cubic centimeter, so it's around 1. So now our program is ready. You could easily calculate now the wet bulk density. Actually, let's calculate the wet bulk density as well. So let's put this formula here. Let's call wet BD. So M total wet minus ter divided by the total volume. Let me copy this here. Wet bulk density of the sample is wet here. I somehow lost the gravimetric water content, so let's just copy here, and let's just write the gravimetric water content of the sample. The sample is in grams per gram gravimetric water content. So I think everything is correct now. There might be some mistakes in the calculators because I'm doing somewhat fast. And now we can just run our program and use it to do our calculations. So you can use this, adapt this for a lot of different applications in soil physics and hydrology. Let's just see if this is correct. Gravimetric, volumetric water content, wet bulk density, dry bulk density. Okay, let's run it. Let's suppose that our sample has 170.0 grams of total wet mass, 156.0 grams of mass, dry mass of our oven drying. Let's say that our tare here, or the mass of the cylinder, is 35. Our cylinder is 5.0 diameter. Our cylinder is 5.0 in height. So now we have the output. The total volume of the sample is 98 centimeters. So the volume of our core is 98 cubic centimeters, 0.2 cubic centimeters. The dry bulk density is 1.23 cubic centimeters. The wet bulk density is 1.37 cubic centimeters. The gravimetric water content is 0.11, and the volumetric water content is 0.14. Okay, you could round these numbers, but I just leave it like that for now. So this is how you do a simple calculator in Python.